Hello everyone. In this video, we will be introduced to what chemistry is. Some people may shy away from this subject because it seems like a very complex world of symbols, math, and other difficult concepts that might seem like torture to some. But it's actually an amazing and beautiful science of stuff, and if you give it a chance, it will not only blow your mind, but give you a deeper understanding of the world around you. This video will be going over these topics. There are timestamps in the description box below if you would like to skip to a certain one. To start off, chemistry deals with the natural world. Chemistry can be a part of your everyday life. For example, fireworks at a parade would be a beautiful example of chemistry in action. The water you drink, the food you eat, and the air you breathe all deal with chemistry. Even the lead in your pencil is made up of the same substance, carbon, as the diamonds and jewelry that you wear. And even the batteries in your car or calculator involve chemistry. So, a knowledge of chemistry is useful to almost everyone because it occurs all around us all the time. So what is chemistry? Well, a definition of chemistry includes it to be the science that deals with how three tiny particles, the proton, the neutron, and the electron, came together into trillions of combinations to form, well, pretty much everything. So basically, chemistry deals with the different compositions and properties of the substances in the universe and the changes that these substances go through. First, we're going to be taking a historical perspective on the creation of the science of chemistry. Chemistry didn't really even exist until a super smart, super wealthy French guy put the puzzle pieces together into a coherent theory for quite literally how everything works. And if you've ever found yourself sitting at your desk reading the same line in your chemistry book for the 30th time in a row, well, you can all credit it to this guy, Antoine Lavoisier. And he is widely regarded as the father of modern chemistry. So Antoine Lavoisier had a pretty interesting scientific and academic life. He was born into a wealthy family and inherited a massive amount of money when his mother died when he was only 5 years old. And though he did get licensed to practice law, as his father expected him to follow into his lawyerly footsteps, young Anton chose science instead. He ended up becoming a geologist, a botanist, a biologist, and a physicist. He helped define the metric system and created an international language of chemistry. He even named hydrogen and oxygen, which are two elements on the periodic table. And he predicted the existence of silicon and even outlined what elements were. He even figured out how animals extracted energy from food and determined that an element could take up different forms upon discovering that both ash and diamond contained pure carbon. He even published the very first chemistry book ever, and there's a reason why the law of the conservation of mass used to be called Lavoisier's law. Here we have the scientific method, and answering scientific questions requires this method. So the scientific method is a process of being able to solve a problem or questions and to prove whether something is or isn't true. And there are numerous steps to the scientific method. The first step is to make an observation or many observations. This is a that's so funny moment or a that's so interesting moment where you wonder why something is the way it is. For example, you're doing your homework and you realize the chocolate bar in your pocket is melting, or you realize the birds outside your window sing a lot, or you observe how on some days it's hot or on other days it's cold. The next step after you've made your observation is to ask questions, and determining which questions to ask is one of the most important steps in the investigation process. Referring to our three previous examples, we would probably ask something along the lines of, why did the chocolate bar melt in my pocket? Or why do birds sing? Or why is the sun so hot on certain days and not on others? Your next step in the scientific method is to develop your hypothesis. A hypothesis is a statement that explains a phenomenon or answers a specific question. It is a tentative or not a fixed explanation for an observation. For example, referring back to our 3 original examples, we can form a hypothesis such as the chocolate bar is melting because it is hot, or the birds sing to communicate. And then for our 3rd example, we can draw up a hypothesis and think that it's hot when I'm happy and cold when I'm sad. Now, it doesn't necessarily mean that any of these hypotheses are correct. The main reason to form one in the first place is to test if they are correct or if there's another explanation to our questions and observations. Next, we make our predictions. So we expand our hypothesis and we make it more descriptive. This is where we incorporate if-then statements. So basically our prediction will be a specific statement that can be tested on. So for original 3 examples, we can make predictions with if-then statements. So for the first one we have, if the body heat from my body is too hot, then the chocolate bar will melt. But if it is kept in the fridge, then it will not melt. And for a second example of why do birds sing, we can make up a prediction and we have this statement. If the birds are singing, then it means they are communicating to mark their territory. And for our 3rd example, for our prediction on why the sun may be hot on some days and not on other days, we could write out using an if-then statement, if I am happy, then it is hot during the day. And if I am sad, then it is because it's cold. Again, it doesn't necessarily mean that any of these predictions are correct. The main reason to form one is to test if they are correct or if there is another explanation to our questions and observations. The next step is to experiment and test our predictions and hypotheses, and we can usually expect 2 possible outcomes. We know our hypothesis at the end of our experiment will either be supported or it will not be supported. And that's what we're going to be trying to find out. So you might think that we're done, but actually we end up making more predictions as we experiment. Then we experiment some more with our new predictions. So this cycle of going back and forth between your predictions and your experimentation is known as collecting your data. We keep checking to see if our hypothesis and predictions are supported. Then we revise our predictions or create new ones and then test those out. Ultimately, our main goal is to end up analyzing this data to come up with our conclusion. Next, we analyze our data. What can we tell about our trials or our errors that happened during our experimentation? And lastly, we tie it all together. We think back to the very beginning of our scientific method process, how we had an observation, asked our questions, made our predictions or our hypothesis, and then experimented multiple times, and then analyzed our data and results. From our data, we determined if our hypothesis was supported or true, or if a different outcome occurred. The more experiments that support the hypothesis, the more confident we can be that it is true. So here we have the scientific method, and answering scientific questions requires this method. So the scientific method is a process of being able to solve a problem or question and to prove whether something is or isn't true. And to sum up the scientific method, we have our 8 steps. And it may vary by some people, but the scientific method usually follows this general outline of steps. So we begin with making an observation, then we ask questions about the observations we made, And from our questions and observations, we formulate our hypothesis and make predictions with our if-then statements so that we can make a testable experiment from it. Then we perform our experiment multiple times, and multiple times is preferred to test if the data we collected is reliable. And from our experimentation, we collected our data that we have to then analyze. And from our analysis, we can form our conclusion. I want to touch up on the difference between correlation versus cause and effect. Sometimes people tend to mix these two up or think the two mean the same thing, but they're actually quite different. With correlation, when two things occur together, it doesn't always necessarily mean one causes the other. So for example here, for correlation, we can say that people tend to spend more in the shops when it's cold and less when it's hot. But it doesn't mean cold weather causes a lot of spending. There are other factors that can play into this situation. Now with cause and effect, when two things occur together, one actually does happen because of the other. For example, if you touch a pan, which is the cause, you end up getting burned, which is the effect. The cause is the reason why something happened, and the reason for you getting burned is because you touched a hot pan. No matter what happens, this will always be the effect. In an experiment, we have different variables, and a lot of scientists conduct controlled experiments by controlling the effects of all variables except the tested one. Often, controlled experiments have a treatment area that is manipulated and another that is not, and this can be called a control or a placebo. For example, someone may want to test if the sugar in a particular type of cookie makes people hyper. So then one group, Group A, will be given the sugar cookie and Group B will be given a cookie without sugar. So our independent variable will be the sugar in the cookies, not the cookies themselves. And then Group A will be the treatment group, and they will get the treatment variable, which will be the sugar cookie. And then Group B will be the control group, and they will be getting the control variable, so the cookie without sugar. And then we end up getting our dependent variable, which is the measured result of our experiment. And it is analyzed in both the treatment and the control groups. So for this example, it will be whether participants in either the treatment group or the control group feel hyper or not after eating the cookie. So matter is an important part of chemistry. It's anything that has mass and takes up space, and it's pretty much the stuff the universe is composed of. Also, matter is composed of even tinier particles called atoms. So for example, a gold coin is made up of matter since it has mass and occupies space. And then the gold coin is made up of even tinier identical gold atoms that are packed tightly together to make up this one big coin. These are three states of matter. There are more, especially if you study more advanced chemistry, but these are the most talked about physical states of matter. So we have solid, liquid, and gas. Solids have a fixed shape and volume, and the particles are tightly packed together. An example of solids would be ice cubes, your hand, your computer, or your phone. Next we have liquids, and liquids take up the shape of their container, so they don't have a fixed shape. However, they do have a fixed volume. Examples of liquids would be the water you drink, blood, milk, soda, juice. And now we have gases for our third physical state of matter. And for gases, there is no fixed shape and there is no fixed volume. So particles move around freely and randomly, as you can see here in the third diagram. So let's dive a little deeper into each state of matter. Here we have some more information on solids. We have already established that solids have a definite volume and shape, and this is because the particles are so tightly packed together due to being held by very strong forces of attraction. Now we have liquids here. Liquids are super weird and super rare, and a fun fact is that only 2 of the 100-something known elements are liquid at room temperature, and that would be bromine and mercury. So, to sum up liquids, liquids have no defined shape, but they do have a defined volume. The particles aren't as tightly packed together as solids, so they move around each other and are a lot more mobile. And an example of liquid would be the water that you drink. And lastly, we have gases, such as the air we breathe, the helium in balloons, or the steam that comes out of the hot mug of coffee or tea that you make. Gases have no defined shape or volume, therefore the particles move around more freely and at random than both solids and liquids. And this is because the attractive forces are so weak that the particles are independent of each other. Now, another phase that I think is pretty cool is plasma. That's when we get a gas really excited and it starts to ionize. So it starts to give off electrons, and then we form something called plasma. Plasma is by far the most common form of matter. Some examples of plasma can be the plasma that's in the stars, or even the plasma that's in the thin layer of space between each one of them. You can even see plasma in fluorescent lights or in a lot of TVs and in some computer screens. Few review questions. We have our first question here, which is asking, which form of water has a definite volume but no definite shape? A. Ice, B. Liquid water, or C. Steam? Go ahead and take 3 seconds to figure out your answer. And we have B. Liquid water. For our next question, it's asking what physical state is found in this container. Is it A. a solid, B. a liquid, or C. a gas? Go ahead and take 3 seconds to figure this one out. And it's going to be C, a gas, and that's because these particles here are moving around freely and they are not tightly packed together. For our next question, we have what physical state is found in this container below? Is it A, a solid, B, a liquid, or C, a gas? Go ahead and take 3 seconds to figure this one out on your own. So we have A, a solid, and that's because the particles here are tightly held together. Okay, so let's take a look at one more review question, and it's asking which 2 elements are liquid at room temperature. Go ahead and think about it for a few seconds. I'll give you 3. And it's going to end up being mercury and bromine. So let's go deeper into classifying matter. We can classify matter as an element or a compound. The elements are what you find on the periodic table, which can be seen on the picture on the right here. So some examples of elements include Na for sodium, or Cl2 for chlorine, or even O2, which is oxygen. And elements cannot be broken down any further into other substances by chemical means because they're already in their simplest forms. And all the matter in the world around us contains elements. Now for compounds, these are made up of two or more elements to make the compound. Now compounds can be broken down because they are different elements brought together. For example, we can combine two elements such as Na, which is sodium, with Cl2, which is chlorine, and this will form NaCl, which is sodium chloride, or more commonly known as table salt. Or we can combine two hydrogens with one oxygen and form water, which is going to be H2O. Matter can be either a pure substance or a mixture. We have pure substances that always have the same composition. For example, pure substances can be an element or a compound. Water, or H2O, will always be water, so it will not be something else. One thing to note, however, is that as we find water in nature, liquid water always contains other substances in addition to pure water, so in this case it will be a mixture. And the same thing can be applied, for example, to metals like gold or nickel or copper. Some jewelry, for example, will have mixtures of different metals, and it doesn't necessarily mean that it is pure gold or pure nickel or pure copper. But when it is in its purest form, it will be considered a pure substance and not a mixture. Now, a mixture, on the other hand, varies in composition. For example, solutions are mixtures. We can have strong versus weak coffee, or a cookie with 5% sugar, or a cookie with 50% sugar in it. So we can classify matter even further as either homogeneous or heterogeneous. Homogeneous is when it's uniform in appearance and the properties are the same throughout. And homogeneous can also be called a solution. So we have examples such as water or Mountain Dew or maple syrup. And then we have heterogeneous matter, which consists of two or more physically distinct phases. And most of the time you can tell there is a difference between the two components. So for example, sugar water, although it might be harder to tell with that one, but there are two different components that make up the sugar water. We have the sugar crystals and then we have the water. And then for trail mix, you can tell it's heterogeneous because you've got your nuts and you have your raisins and your M&Ms that make it up, and you can tell there's a difference in all the material that trail mix is made out of. Another example would be pizza. For example, the pizza here on the right, you can tell that there are carrots and tomatoes and broccoli and cheese and bread and onions, so it all looks different. So that means it's heterogeneous. You can tell there is physical distinction between the components of the pizza. This is a chart that pretty much sums up the classification of matter depending on its properties. A given substance can be classified as either homogeneous or heterogeneous, a compound, or an element. So if you want to classify whether matter is any of these, you can ask yourself the question if if the properties are constant or have constant composition, and if it's a yes, it's a pure substance. And if you want to further determine if it's a compound or an element, you can ask the question if it can be simplified further. And if it's yes, then it's a compound. If it's no, it's an element. Now on the other side of this chart, if you ask the question if it's a constant composition or constant property and you get a no, then it is a mixture. And if you want to determine if it's homogeneous or heterogeneous, you can ask yourself the question if it's uniform throughout or if the properties are same throughout. So if the properties are the same throughout or if it's uniform throughout, then it is homogeneous, but if it's not, then it's heterogeneous. Now let's take a look at the different properties and characteristics of matter. We can classify it as either physical properties and characteristics or chemical properties and characteristics. So let's start off with physical properties and characteristics. Physical properties mean that the characteristics or the chemical composition of a substance doesn't change. So the substance is still the same and doesn't become another different substance. For example, we have wax, and it undergoes a physical change when solid wax is heated and it forms liquid wax. Either way, it's still wax and it doesn't become a new substance. Or we have steam when a cooking pot boils, and it's considered to be a physical change because the liquid water becomes a gas, which is the water vapor. And the water vapor can still be turned back into a liquid form of water. Thus, the water is still water and it hasn't changed into a new substance. Now, when you want to determine or look for the physical characteristics, we can determine it by using our senses. So we see what color the substance is, if there is a smell, what does it taste like, whether it is a solid, liquid, or gas, if there's a melting point or a boiling point. So these are some examples of physical characteristics. So here is an example of a table of 3 substances and what we would normally look for if we're looking at any physical properties or characteristics of a substance. So for example, we have sugar water. You can describe the color as being clear or cloudy, the odor as being odorless, the taste being sweet, and the physical state being a liquid, and then we have the melting point and boiling point information. And then the same can be applied to the other 2 substances listed below. Now, it doesn't necessarily mean that you'll want to state all physical characteristics. For example, it's normally advised against to taste substances, so in some instances you might want to leave that one out. So when talking about how for a physical change no new product is formed and that it is generally easily reversible, for example boiling water or the freezing of water, well, in contrast, when we talk about a chemical change, there is always the presence of one or more new substance at the end of the change, and it is generally not easily reversible. For example, when metal rusts, such as in the first picture on the left, it means there is a chemical change that happened due to rust being a different kind of matter than the original metal. Or if we're cooking something, for example, or toasting something like bread, it would be hard to reverse it back to its original state. So we see the bread's original state, and then if you toast it or burn it, then it will be really hard to reverse it to its original untoasted or unburnt self. If you enjoyed this content, please consider subscribing to help support the making of more videos. Thank you and see you in the next video.